Now we want to discuss today Lloyd's single mirror experiment. There are also Lloyd's double mirror experiment, but we will not discuss the things which is not in your syllabus. Only we will discuss Lloyd's single mirror experiment. So how coherent sources are produced in Lloyd's single mirror experiment, that we will consider first. So actually in Lloyd's mirror experiment, the source is present at a certain height from the plane of the mirror. Now this is the mirror, plane mirror, and this is the plane of the mirror, and above that source is present. Now this separation is, we can consider d by 2, small d by 2. Then what will happen, from this source light will fall on the screen directly. The direct beam will fall on the screen, and another light beam, that is the reflected beam, fall in this region. Right? Another reflected beam, light beam, will fall on this mirror, on the screen by through reflection on this mirror. Right? So now you consider the screen is occupied by two light beam within this region. This region, one is direct beam and another beam is present in this region, that is reflected beam. So only this portion is occupied by two beam. One is direct, another is reflected beam. Now you consider, if we observe this reflected beam, then we can observe it is coming from this region, somewhere in this region, right? So this can be considered, or this point can be considered as the image of this source S, right? So this is the virtual image. So it can be considered as the virtual source. So in this situation, we will get two beam. One is direct beam from S, another is reflected beam that may be considered it is coming from S prime. That is the virtual image of S. So here we get two light beam. So when we get two light beam, then there is a possibility of interference. And obviously here we can also observe the interference pattern, right? Now, if we move this screen, now another thing, before changing the position of the screen, we can consider the what is the path difference between these two beams. One beam is direct beam, another beam is reflected beam. So whatever may be, if we consider any point on the screen where interference pattern is produced, at that point the path of the direct beam is always less than the reflected beam. You know these things, that the reflected path is always greater than the direct path. So in this situation, we can observe the interference pattern, but we cannot get the zero path difference. In young double slit experiment, Lloyd's mirror experiment, we have got the position of zero path difference. In the position of zero path difference, that will give you the intensity maxima. Maximum intensity will occur at zero path difference position. But in this situation, the direct path is always less than the reflected path. So we will never get the zero path difference. That means we cannot observe the central field. According to this experimental arrangement, we cannot observe the central position. Now, if we move this screen towards the mirror, if we move the screen towards the mirror, and if it will touch at this position of the mirror, at the end of the mirror, if the screen will touch at the end of the mirror, then what will happen? At that particular point of contact, that particular point of contact, the path difference will be zero. That means the reflected path and direct path will be same at the position of contact between the end of the mirror and the screen. So in that situation, if we observe the pattern, fringe pattern, then we can observe that it is a dark fringe. Experimentally, it has been observed that it is a dark pattern, right? That position will gives you the dark pattern. That means when the path difference is 0 in Wright's mirror experiment, that indicates the phase path difference is 0, but that indicates the minima. But according to our previous knowledge, it should be maxima. Then what will happen? So actually, in this situation, at the point of contact, one beam, that is a reflected beam, undergoes a phase shift of pi. The reflected beam undergoes an abrupt phase shift of pi. So that is why, which is equivalent to path difference is lambda by 2, right? Which is equivalent to path difference is lambda by 2. So that is why we observe the dark ring at the position of contact, right? But in previous case, at the position of 0 path difference, it is maxima. But in case of Lloyd's mirror experiment, at the position of 0 path difference, that will gives minima due to the abrupt phase change by reflection by the mirror. That means when a light beam undergoes a reflection backed by a denser medium, then it undergoes a phase shift of pi. We always remember that when a light beam undergoes a phase shift of pi, then it must reflected back by a denser medium. Can you remember this point? So that is why we will get the minima at the point of contact. Now, this can also be explained mathematically according to Stokes' relation. So now we consider the Stokes' relation. Now we consider there are two medium 1 and medium 2. And this is the interface. Now a light ray of amplitude A, falls on this interface at O. Then what will happen? A part of the light beam will be reflected back in the same medium, and another part will be transmitted to the second medium, right? Now, if we consider the reflection and transmission coefficient from medium 1 to medium 2 is A and T. We consider the reflection and transmission coefficient from medium 1 to 2 is A and R. Then the amplitude of the reflected beam will be AR and the amplitude of the transmitted beam will be AT. Now, if we reverse these two beams, then what we will get? We must return back this incident beam. If we reverse this reflected and transmitted beam, then we must get the incident beam, because you know that optical path is reversible. So under that condition, if we reverse both the beam, reflected and transmitted beam, then it must retrace the path of the incident beam with same amplitude. Now, suppose we reverse AR, this beam. We reverse this beam. That means this is one beam from this point at O, and its amplitude is AR. Then what will happen? This beam will gives you one reflected beam and another is transmitted beam. So the reflected beam will be amplitude AR square. The amplitude of the reflected beam will be AR square, and the amplitude of the transmitted beam is ART, because reflection and transmission coefficient from medium 1 to 2 is R and T. So this is AR square and this is ART. Now, if we reverse that, the transmitted beam AT, this amplitude AT, then again it will produce a reflected beam and transmitted beam. The amplitude of the reflected beam will be AT R prime. Now we are considering R prime and T prime are the reflection and transmission coefficient from medium 2 to medium 1. From medium 2 to medium 1, we consider the reflection and transmission coefficient R and R prime and T prime. So this beam of amplitude AT, it will produce one reflected beam ATR prime and transmitted beam ATT prime, right? So now if we add these two amplitude, that is ART plus ATR prime, that is equal to 0, because initially there is no beam in this medium. So that amplitude, sum of these two amplitude will be 0. That is ART plus ATR prime. This is 0. And if we add these two amplitude, that is AR square plus ATT prime, that must be equal to A, because there is a incident beam of amplitude A. So that means AR square plus ATT prime equal to A. So under this situation, if we write it here, then we will get TT prime plus R square equal to 1. And for this ATR prime plus ART, that will gives you 0. That means R prime equal to minus R. That is R prime plus R equal to 0 or R prime equal to minus R. Now, here TT prime equal to 1 minus R square. That we can write TT prime equal to 1 minus R square. Now here, according to this equation, R prime equal to minus R, but we cannot write R equal to minus R prime. R prime equal to minus R, we cannot write R equal to minus R prime. The negative sign indicates pi phase change occurred due to reflection when light reflected back by a denser medium. This second medium is the denser medium. Here we have considered that second medium is a denser medium, so it undergoes a phase shift of pi. So due to this phase shift, we will get this negative sign. So that means R prime equal to minus R. That means it indicates the second medium, that is the denser medium. So we must put a minus R. Point is clear? Can you understand this point? Hello? ভর্তি তো হবে। ওই যে রেফারি দিতে হবে, দুজনের নাম দিতে হবে তোকে। সে একবার আগে দিসনি, লালটর নাম আর কার্ড দিয়েছিলিস যে, সেরকম তার নাম, অ্যাড্রেস, মোবাইল নাম্বার, এই সমস্ত সেরকম পরিচিত, সে কি করে, তার ডেজিগনেশন, এই সমস্ত। কিন্তু তাদেরকে বলিস কনসেন্ট নিয়ে তাদের নাম দিস, কারণ তাদেরকে ফোন করতে পারে। হ্যাঁ, মেল, ফোন নাম্বার সব লাগবে, এটা দেখিস। Okay, so R prime equal to minus R. That indicates this beam will reflected back by the denser medium. So it indicates an abrupt phase shift of pi. That is the evidence. Okay, now we consider measurement of thickness by using double slit experiment or by prism experiment. Basically, we consider double slit experiment. There are two slits, S1 and S2. Their separation is D. So if we put one transparent material of thickness T of and refractive index mu, then what will happen? Initially, when this material is absent, then your central spot is present here. But when we put this material, then your central spot will be located in some region, right? Somewhere in this region. Because for central position, the path difference is 0. So if we introduce some extra path in one of the beam, then other beam will also consider that same amount of path. So that means your O will be shifted in this region, somewhere in this region. So we consider the position is this O, right? So now under this condition, this is S1P or without flame, that is S1O, that is equal to S2. But in presence of that, this path is extra compared to this path, this S2. So that's mean it will shifted to somewhere in this position. Right, now we can write S2O prime, that is S1O prime, that indicates what is the extra path here. Extra path, that means the thickness of the flame is mu, T, and refractive index mu. So the optical path length inside this material, that is mu into T. So optical path length is mu into T. Now, if this plate is absent, then it will traverse the path only T. In that situation, in the absence of plate, then it can also goes through the path T. But in presence of this material, it can moves the path, optical path length, that is mu into T. So the extra path, that is mu minus 1 into T. The extra path is mu minus 1 into T. That is mu T minus T. That is mu minus 1 into T. So this extra path is S1, S2P minus S1, right? Or S2O prime minus S1O prime, right? That is equal to mu minus 1 into T. And if this point is located at a distance of x0 prime, right? X0 or x0 prime, that is x0 d divided by capital D, that is equal to mu minus 1 into T. And if we consider this is the position, 0th position initially was 0th order maxima, right? That is central maxima. Now this maxima is shifted to the position of nth order maxima. If this maxima is shifted to the nth order position, or nth order maxima position, then we can write mu minus 1 into T, that is equal to n lambda. Mu minus 1 into T, that is equal to n lambda, right? So under this situation, we can write mu minus 1 into T, that is equal to x0 d divided by capital D, or equal to n lambda. So by using this formula, we can determine the position, the shifted position of the central maxima, or we can calculate the position of the shifted maxima at which position of the other fringe position, right? Or overall shifting of the fringe pattern, that we can determine, right? According to this. Now this I will not discuss. So this part is completed. That is interference pattern by division of wavefront. Next, we will consider division of amplitude. So before going to that, there are few problems I have already mentioned here. This is a very simple problem, and how to solve I have already mentioned. The hints to sources of intensity 4I and I are used in interference experiment. Calculate the resultant intensity at point with phase difference 0, pi by 4 and pi. So I have already written the formula, the intensity I1, I2 cos delta, that is phase difference, right? So if you to put this data, then you will calculate. The amplitude of light field of two slits In Young experiment, in the ratio 1:2, calculate the ratio of maxima intensity and minima intensity. So maxima intensity and minima intensity, that is root of I1 plus root of I2 square whole square, then root of I1 minus root of I2 whole square, right? And here I1, I2, that is, it is given in the amplitude ratio, that is A1 by A2, that 1:2, that means A1 square by A2 square, 1:4. So if you put it, then you will get the value. Then again, the path difference at a point on the screen is lambda by 7. It is given. And the interference pattern, calculate the intensity with respect to its central bright spot. So that intensity is I, that is I divided by I naught, that is 2 into 1 minus cos delta. Here delta is given twice pi by lambda into path difference. Path difference is 2 lambda by 7, right? So then you will put this is delta and you will get the value. Then it is fringe width calculation. It is D and beta calculation in biprism, right? So these are the simple mathematical relation that I have already mentioned here, and based on that you can calculate the result, right? There are 8 problems I have given. Can you understand this point? Are you present in the class or there is no response from your side? Nobody is responding. Very good. Okay, whatever maybe, I will finish my work. So now we consider interference by division of amplitude. Now, in previously I have already mentioned that in case of division of wavefront, a narrow slit source is required. But in case of division of amplitude, we always need an extended light source. So how it is required, or why it is required extended light source for division of amplitude? Basically, we have already mentioned in the condition of interference that there must be two beam of almost same intensity. Both the beam must have almost the same intensity to get the maximum visibility. So now in case of division of amplitude, the amplitude of the light beam is divided into 2 parts, and that is responsible for interference pattern, right? So in this situation, if we use a narrow source, then the amplitude will be divided, and then the amplitude level of the 2 beam will be considerably small amount, and that will beyond detectable. So this is the difficulty to understand the interference pattern. That is why in case of division of amplitude, we always need extended light source. So when we consider extended light source, that its amplitude is large amplitude beam. So when we divide it by almost 2 equal halves, then it will satisfy the condition of interference, and at the same time we will get the maximum visibility. But in case of narrow slit source, the visibility decreases, and that may be beyond detectable, right? So that is why we need extended light source. Now, how we will calculate the path difference in case of extended light source? Now, first of all, we consider the reflected beam from a glass plate. We consider the reflected beam from a glass plate. Now here it is a glass plate of refractive index mu2, and in this surroundings medium, the refractive index is mu, and mu2 is greater than mu1. That means this is the denser medium. This is the denser medium. So when we consider an reflected beam, then it undergoes a phase shift of pi. It undergoes a phase shift of pi because it is reflected back by a denser medium, right? Now we consider a beam AB fall at point B on this interface, and then it will produce one transmitted beam, another reflected beam. So the first reflected beam is CD. Then again, the transmitted beam will produce one reflected beam at point E, that is EF, and it also produced another transmitted beam. It also produced one transmitted beam. That beam is somewhere in this region. Then at point A, again there is a transmitted beam, that is FG, and another reflected beam FH. And from point H, there is again a reflected beam HI and a transmitted beam in this region, right? And so on. So like this way, we will get a number of reflected beam in this region, and at the same way, we will get a number of transmitted beam also in this region. So this beam will be divided into two beam, that is, one is reflected beam, another is transmitted beam. But in case of reflected beam, there is a large number of reflection will takes place, right? And similarly, a large number of transmitted beam we also get in this region. Now we restrict ourselves within the reflected beam. So now in each reflection, then we can consider the amplitude is continuously decreasing, because you know the reflection coefficient that is reflected beam will produce if it is initial amplitude is A, then AR, then AR square, and like that way it will produced. That is AT, ATR, or like that. Like this way we will get the amplitude of transmitted beam. Now consider two successive or two consecutive reflected beam. For example, if we consider CD and FG, if we consider these two consecutive or two first two reflected beam, then these two beam are always or almost equal amplitude. These two beam is almost equal amplitude. If we consider that is CD and IJ, this beam amplitude is reducing, right, compared to this. But these two is almost same, right, amplitude. So we consider this first two reflected beam, and if we unite them by some means, that is lengths, because these two are parallel. If we unite them by some means, that is by lengths, then we can observe the interference pattern at that point. We can observe the interference pattern. Now we consider what is the path difference between these two consecutive reflected beam. Now here you see up to point B, that is at the point of intersect in this interface, this point B is same for both the beam, that is CD and FG. So now these two beam is parallel beam. So if you draw one normal from F to BD, if we draw one normal from F to BD, then what will happen? The path from CD and FG are equal. At the point of, suppose some point is P here, which the point of interference. So CP and FP, this is the same path, equal path. So there is no path difference. So path difference is introduced in this region. So now here from point B we will get the beam CD, and this is the extra path. For this beam we consider, and for this beam there is the path, extra path, that is BE and EF in this median, right? So the total path difference between these two beam, that is BE plus EF multiplied by mu2 minus mu1 into BC. This is the path difference. So path difference between these two interfering beam, that is mu2, that is BE plus EF, right? BE plus EF multiplied by mu2 minus mu1 BC. Now from this simple mathematics, we can write the path difference in this form, that we will see. Now this you see here, that is BE equal to EF, because you see this angle is R, so this angle is again R, right? And this is the normal in this point. So this angle 90, this angle 90, right? And this is the common. So these two will be congruent. So this will be is equal to this. So that we can write, that is B equal to EF. And this equal to T divided by cos R. If we consider this angle is R, then that is BE or EF, that is equal to T divided by cos R, where T is the thickness of this slab. T is the thickness of the glass plate, right? T is the thickness of the glass plate. Now, BF, this quantity. So from this term, we can write mu2. This is 2 into T divided by cos R, that we can get. And from mu1 BC, that BC, that is equal to BF sin I. That is BC, that is equal to BF. This angle is I. This angle is 90. This angle 90 is this angle. This angle 90. This is I. So that is we can write BC, that is equal to BF sin I, and BF, this quantity, that is equal to twice, that is twice T tan R, twice T tan R. This, if we consider this angle, this is R and this is BA, that we can consider as half of this. Then we will multiply it by 2, right? So that is T tan R, then multiplied by 2, that is 2T tan R. So if we put it here, that is twice T tan, that is sine by cos, and again this mu1 twice T sin R by cos R, then mu2 by mu1 sin R. Okay, this sin R, that is mu equal to sin I by sin R. Mu equal to that is sin I by sin R in this region. If we consider sin I by sin R, that is mu2 divided by mu1. So mu2 divided by mu1, that is sin R, right? In case of sin. Then you can see this mu2 will be cancelled out. Then sin square R by cos R. So if we take common, that is mu2 twice T by cos R, 1 minus sin square R, that is equal to cos square R. So cos R will be cancelled out. So we will get twice mu2 T cos R, right? So this is the actual path difference, twice mu2 T cos R. So when we consider a glass plate, then the path difference between two reflected beam, first two reflected beam, that path difference is twice mu T cos R, where R is the angle of refraction, right? and mu2 is the refractive index of the second material, right? So if this condition satisfy the condition of maxima, then we will get the maximum intensity at the point of interference. If this will satisfy the condition of minima, then we will get the minimum intensity at the point of interference. Now, considering another thing, that is, if we consider this refractive index is mu2, then twice mu2 cos r equal to n lambda condition of minima. N lambda condition of minima, because one of the beam undergoes a phase shift of pi. That is first beam. First beam undergoes a phase shift of pi because it is reflected back by the denser medium. But the second beam is reflected back by rarer medium. So the first beam undergoes a phase shift of pi. So it will gives you the condition of minima when this path difference that is equal to n lambda, right? That is twice mu t cos r, that is equal to twice n minus 1 lambda by 2. That is the condition of bright fringe. And condition of dark fringe is twice t. Yes.
Sir, when to consider 2n plus 1 lambda by 2 or 2n minus 1 lambda by 2?
Here you see actual path difference is we have calculated twice mu2 t cos r. Then if we consider the path difference due to this phase change at this point, that is CD, phase change is pi. So that corresponding path difference is lambda by 2. So the total path difference between these two beam is twice t mu2 cos r plus lambda by 2. Then we can write the condition of maxima, that is n lambda, right? So if we move this lambda by 2 in this side, then we will get this result, twice n minus 1 lambda by 2.
Sir, but we are minusing mu1 BC. So, sir, in BC part, additional phase difference, so minus lambda by 2 it will be there now, because we are subtracting second ray from first ray, like that.
Which one?
And the phase difference is in first ray, so it will be, yes, sir, we are subtracting like mu2 BE plus EF minus mu1 BC. So, sir, we are subtracting from first ray. So, sir, it will be minus lambda by 2 now, because yes, sir. In the
Okay. Yes. So under that situation, it will be plus. Yes, you are right. So under that situation, we are subtracting from this path minus this path, right? So it is extra path, and at the same time the phase difference, that is pi, which is equal to lambda by 2. So we must subtract, that is lambda by 2. So if we put here minus lambda by 2, then we will get this is plus. Okay, this is correct. So we can write here twice t mu2 cos r, that is twice n plus 1 lambda by 2. That is the condition of bright fringe, right? Is it okay?
yes, sir. Sir, just one thing, sir.
Yes.
When we are like originally considering like dark fringe, so sir, what we will take, 2n plus 1 lambda by 2 or 2n minus 1, or doesn't matter which one we take?
It does not matter. It will does not matter anything. Okay. So whatever you will write, both are correct. That is not the problem. Okay. Or simply you can see this is the condition of bright fringe, right? That is odd. This quantity is odd, lambda by 2, and you see this is the even lambda by 2, right? This is dark fringe. It will be the even multiple of lambda by 2. That you should consider, right? Initially in young double slit or biprism experiment, that is maxima will be appeared at even multiple of half wavelength, and minima is odd multiple of half wavelength. But here it is reverse. Why it is reverse? Because due to a phase shift of pi, of one of the interfering beam. Point is clear?
Yes, sir.
Okay. So we'll stop it here. Same things. Okay, another thing we will mention in the transmitted beam. The same mathematical treatment we have to do for the transmitted beam. That is up to this portion, up to C, it is the common part. And then you see one is reflected, transmitted here, another reflected, then again reflection, again transmitted. Right? So if we unite these two transmitted beam, then what we will get? We will get the same path difference. That is twice mu to t cos r. The same path difference we will get here. Now here you see there is no abrupt phase shift between these two beam. Right? So in this condition, the condition of maxima or bright fringe will be twice n lambda by 2. The condition of maxima will be twice t mu 2 cos r, that is twice n lambda by 2, and the condition of minima, that is twice t mu 2 cos r, that is equal to twice this is n twice n plus 1 lambda by 2, right? Twice n plus 1 lambda by 2. So the condition of maxima and minima will be reversed in case of transmitted beam and reflected beam. In case of transmitted and reflected beam for a glass plate, the condition of maxima and minima will be reversed. That is complementary each other, right? Because one of the interfering in one case, either in reflection, there is a abrupt phase shift of pi, but in case of transmitted beam, there is no phase shift, abrupt phase shift. So the condition are reversed, right? Point is clear?
Yes, sir.
So I will stop it here. You will see, and next class we will continue from OS shape flame. Okay. So I will stop it here today. Okay. Thank you all.
Thank you, sir.
Okay. One thing. Today I will take your another practical. Okay. At 3 p.m. You have practical. So I will take another practical today at 3 p.m. But today class will start at 3:15. Okay. So you can join at 3:15. I have scheduled at 3, but today we will start at 3:15. So you remember this time and you join at 3:15. Practical. Okay.
Okay, sir. Thank you, sir.
Thanks.